The ultimate goal of condensed phase chemistry is to predict exactly how atoms interact and bond at the quantum level. If we can see those mechanics perfectly, we can engineer entirely new drugs, batteries, and materials from the ground up. The standard approach is through first principles simulation. This means calculating the physics from scratch without relying on empirical assumptions. The problem is the math. Solving these quantum mechanical equations for large groups of atoms takes an agonizing amount of supercomputer time, often limiting scientists to simulating just a few hundred atoms for tiny fractions of a second. Researchers are caught in a strict mathematical trap between expressivity and efficiency. Simplify the simulation to make it run fast, and the model loses its physical accuracy. Demand perfect quantum accuracy, and the simulation slows to a crawl. Scientists attempted to fix this using machine learning interatomic potentials, or MLIPs, training AI to predict atomic forces rather than calculating them from scratch. But even foundation models with millions of parameters run into trouble. When they encounter rare, complex events, like a chemical bond actually snapping in half, the computing demands spike and the models stall. We possess the equations required to observe rare quantum events. We just lack the computational bypass to run them without exhausting our available computing power. To escape the expressivity efficiency trap, researchers have developed a two-step algorithmic bypass. Step 1 is transfer learning. Scientists start with a high-capacity foundation model and fine-tune it on a very small set of perfect first principles data. This creates an accurate but computationally heavy teacher model. The teacher knows exactly how the physics work, but it remains incredibly slow to run. Step 2 is knowledge distillation. The teacher model is used for exactly one job. It generates thousands of synthetic data points based on its perfect physics knowledge. Those data points are then used to train a secondary, much smaller artificial neural network. The result is a lean student model. Because it learns strictly from the teacher's perfect data, it retains the physical accuracy of the heavy model, but it operates at a fraction of the computational cost. The math suggests this should work, but to be trusted by the scientific community, the student model must survive a gauntlet of 3 escalating physical states. Test 1 establishes the baseline, ice, a rigid crystal lattice where atoms vibrate predictably in place. This scatterplot tracks the speed and accuracy of the models. The distilled student models, represented by the circles, successfully predicted the density of the ice while running 10 times faster than the original teacher model. The models passed the static test, so researchers moved to liquid water. Liquids are chaotic. Simulating them requires mapping molecular flow, thermal fluctuation, and quantum proton delocalization, where protons physically wander outside their strict atomic boundaries. The test parameters here were rigorous. The student model had to accurately track the density and diffusion of liquid water across a wide temperature gradient, from a freezing 240 Kelvin up to 370 Kelvin. Looking at these charts for the density isobar and the self-diffusion coefficient, the student model's predictions align with the experimental data. It captured both classical mechanics and quantum nuclear behaviors across the entire temperature spectrum. As you can see in this bottom right plot of nuclear kinetic energy, the student tracked complex quantum fluctuations in the hydrogen and oxygen atoms. Mapping this much data across such a broad temperature range was only computationally viable because of the student model's raw speed. With static solids and chaotic liquids mastered, the architecture is proven stable. That sets the stage for the ultimate test, a live chemical reaction. Test 3 drops the student model onto a titanium dioxide, or TiO2, interface. This graph on the right details the classical free energy profile for water dissociation. Simulating an actual chemical bond breaking on a metallic surface is the highest level of computational difficulty. Looking at the structural model on the left, the roadblock here is that the simulation must accurately model the water splitting apart right at the boundary of the titanium surface, while accounting for quantum fluctuations. Heavy models struggle with the sampling required here, but the distilled student model is fast enough to run path-integral molecular dynamics. This method calculates multiple quantum pathways simultaneously, allowing the student to handle extreme quantum states in real time. By running the simulation for nanoseconds rather than picoseconds, the student model uncovered a physical phenomenon that slower, heavier models could not reach. The successful simulation of the titanium dioxide surface resolved a mystery regarding exactly how water splits. This free energy profile charts the exact energy required to break the water molecule. The dashed curve shows the student model's output. Quantum nuclear effects actually lower the energy barrier for water dissociation by roughly 2 kilocalories per mole. Understanding the mechanics of water dissociation at this precise level is a requirement for applied chemistry. These are the physical interactions driving advancements in catalysis, environmental remediation, and clean energy technologies. Knowledge distillation is a mathematical lens that makes the invisible visible. By shifting the computational burden to an agile student, scientists finally have the throughput necessary to simulate complex reactions and identify candidates for next-generation catalysts. If you found this breakdown helpful, please like, subscribe, and leave suggestions in the comments. Today's video was brought to you by Synestec Systems LLC, founded by Shane Persinger.